this percentage among all the female participants.
Congratulations. Wow.
Yeah.
So cool. Did you do it?
It's my first time.
What was your time? What was your time?
1 hour and 45 minutes.
It's
Good. Okay. All right, thank you everyone for coming today. Today we have Renaud Raquépas from Duke University, and he'll tell us about random and ergodic attractors for diffusions with degeneracies.
Thank you very much, Ben, for the introduction and also for the invitation. It's a great pleasure to be here and talk to you about this joint work with Yuri Bachman and Lai Sang Yang, who were the people I was working with at NYU before moving to Duke. So to introduce the kind of questions that I'll be asking about, I want to start with a very basic example. And so I'm just going to write down one of the simplest SDEs you can think of. Okay, so just think about a diffusion on the circle. So here's a circle. That's sort of laying on the ground because I'm going to draw things on top of it. What do you need to define a diffusion? In one dimension, you need a vector field or a drift. Okay, so I'm going to assume that along this circle, there's a vector field that's, small in some places, big in some other places. This maybe turns around. So that's B is a vector field on the circle. And at every point of that circle, you also have a intensity for the noise. So I'm going to draw this like this, saying at every point above the circle, there's sort of a noise level. There could be places where there's a lot of noise and places where there's not a lot of noise. So I'm going to use sigma for the noise. So now let me write the equation. Okay, so you start somewhere at some point X on the circle, and then that would be just following the ODE for the vector field B. And what makes it a diffusion is that on top of that, there's this random term, sigma of xt dw. So you start somewhere, you want to follow these blue arrows, but you get moved around a bit. That's what an SDE is. Okay.
Did you write the O on purpose?
This?
Yeah.
This is Stratonovich, yeah. It just makes some formulas nicer. Yeah, in Stratonovich form. Okay, and the questions, the kind of things I'm interested in is what is the long time behavior of solutions to this? Okay. And I'm going to probe this large time behavior by looking at two objects. So one of them is going to be the set of limit points of x of t. And if you want to, I'll do this once, I'll write it, but then after that, I'll just say set of limit points, right? So it's just the intersection over all times of the closure of this, right? So the way you should think of this is just a set of points that you come very close to very often, okay? And it has a precise meaning. And I'll do the same thing for the set of limit points of so-called empirical measures. Okay. So I'm going to introduce this measure mu of big T as a time average of measures. Okay, so mu of T is a measure that's waiting for a set to give a measure to, and it just tells you, normalized by the total time, how much time you've spent in that set, right? So that's the empirical measure. And here, when I talk of limit points, I always mean in the weak topology. Okay, so I have a process, and I'm interested in where it goes and where it spends time in the long run. Okay, so those is basic kind of questions that I'm asking. And here, because this equation is quite nice, we can make clean statements about how these two things behave. Okay, so assuming that B is smooth, and that sigma is smooth and positive, you can prove the following two facts. This here I think I prefer right closer to this. That's just the whole circle. You keep exploring the whole circle for F. And the set of limit points of these empirical measures is a singleton. So there exists some probability measure pi on S that has full support and which is absolutely continuous with respect to Lebesgue. And to be precise, I'm going to say Lebesgue on the circle. Okay.
So in these two statements, omega almost surely.
Okay, so now I'm going to start being more precise about what I mean here. So this is here. What is the order of quantifiers, or at least one order of quantifiers that you can easily prove, is that right, the preamble to this would be for every x in the circle, almost surely this happens. So as you said, this a priori is a random object, and it's a random object that depends on where you started. But for every starting point, almost surely that's the set of limit points. And same for this. Okay, so I'll omit this further on. Okay, you can ask if you are not sure, but most often when I write a convergence result, it will be for every x, almost surely. Yeah. And I'll do even worse than that here to express this in short. I'll write something like x of t converges to the circle. Okay, when I say the trajectory converges to a set, I mean the set of limit points of this is equal to what I put on the right. Yes?
Sorry, are you asking that pi is also out to continues to be the Lebesgue measure on circle? Is that what the statement?
It's going to be the fact a fact
Okay,
here.
so it
Yeah.
can't be a-
No, in this case, no. Yes?
Presumably pi is independent of x as well.
Yes. That's also something that you can say. Yeah, So here you could put the there exists before all of this. So there is a measure that lives on the circle that governs the large time statistics of trajectories. And this measure doesn't care about where you started or the particular realization of the noise. Any other questions on those statements? Okay, so as I said, to be economic with space, I'll write just xt converges to a set, meaning that set is the limit, the set of limit points of that. And here I'll write ut converges to emphasize that this a priori could have many limit points. There's one limit point, so there's a limit, and that limit is a pi. Okay. Okay. So the presence of a uniquely determined invariant measure pi, right? So uniquely determined, no matter what the starting point is. The presence of a uniquely determined invariant measure pi, describing large averages. It's not something that's particular about diffusions on a circle, right? It's a thing that happens in a lot of equations. And typically, what you could say is that you're guaranteed to have that happen. That's a common thing to all sufficiently regular non-degenerate diffusions on compact manifolds without boundary. So sufficiently regular just means you make some smoothness assumption. Here, of course, smooth was a bit overkill with some smoothness assumption. So differentiable enough times, for example. Non-degenerate is this assumption that I made here that there's noise at every point, but there's no point where there's no noise, where this Brownian term is being multiplied by 0. And the fact that it's a compact manifold without boundary, well, the circle is a compact manifold without boundary. But if we were to write a very similar equation on the torus, and the noise was sufficiently non-degenerate, and the coefficients were smooth, you would have a very similar behavior. There would be a measure that lives on the torus, is absolutely continuous with respect to Lebesgue on the torus, and almost all empirical measures converge to that measure. Okay. Okay, but that's a few assumptions, right? There's regularity. I'm not going to touch that one. I'm not really in the business of looking at equations with rough coefficients. It's a thing that you can try to push. This is not the direction I'm going to be going in. I'm going to challenge this assumption here and this assumption here. Okay. It should be noted that sometimes you can trade one assumption for the other. So, you know, if you're on the open interval, you can make it compact, but then by making compact, you maybe make something degenerate, or but there's a trade-off. So I decide to push these two, but it can be seen as equivalently as maybe making things unbound. Okay. So there is a huge literature on weaker sufficient conditions for this type of behavior, and I will call this unique ergodic attractor scenario. Okay, so by unique ergodic attractor, I mean that there's a uniquely determinant thing, namely the circle, that all trajectories visit, and it supports an ergodic measure that describes the long-term statistics. So there's a literature on, for example, how much can you push this notion of non-degenerate, right? The whole theory of hypoellipticity and so on, how to deal with boundaries and still have that. That's the topic of a lot of work. But I want to talk about something else. What I want to talk about I want to study alternatives to the universal ergodic attractor scenario. Okay, so I know that I could push these conditions a bit and still have a uniquely ergodic attractor, but I'm interested in understanding what kind of mechanisms in a diffusion can lead to the failure of a dynamical picture like that. Okay, and I'll start with low dimensions. The motivation for this, or a motivation for this, is systems like this, right? Why would I care about what happens when I have boundaries, when I have degeneracies and stuff like that? One example that you can keep in mind is if you have either systems with ecological populations or quantities of two species in a chemical reaction, right? There's naturally a boundary, which is that quantities of populations cannot go negative. There are corners, there are stuff like that. And furthermore, there's a, right, you could also have 3 population if you want. There's a lot of so-called scalable systems like this, where for many intents and purposes, a lot of things only depend on the relative fraction of the 2 population. So what you would do is you would essentially project to this line, right? Technically, the populations, they move in this quadrant, but if you only care about something that has to do with the relative fraction, or same here, if you're in 3D and it moves, but you only care about the relative fractions, that's a simplex. So there seems to be a situation in chemistry and in biology where you have some things that behave like a diffusion, but the way it behaves is not consistent with that kind of scenario. And it seems like it's because of this presence of these boundaries that corresponds to maybe one species being absent. And this seems to be causing new interesting dynamical behaviors that don't fall into this category. So that's one of my motivations for studying these systems. Yeah. Part 1. The closest thing to this that has a boundary would be you cut the circle to make it a line. And again, I'm here. And on the line, I have a vector field B. and I have a noise intensity. Okay. So let me, I'm not going to rewrite the equation because it's going to be the exact same equation. So I'm not rewriting it, but I'm looking at the same thing. But my assumptions will be different. Okay. Okay, so I'm going to, again, assume a form of smoothness. V and sigma extend smoothly. Okay, to make fixed samples, my interval will be 0 to 1. So these coefficients extend smoothly to a slightly larger interval. Okay, so that's a regularity assumption. And I'm going to assume that I want the interval 0, 1 to be preserved under the SDE because I want things to make sense. But I'm also going to assume that the interior itself is invariant and that the endpoints are invariant. And again, this is an almost sure statement. Almost surely, if you start in the closed interval, you stay in the closed interval. If you start in the open interval, you stay in the open interval. If you start at 0, you remain at 0 forever. If you start at 1, you remain at 1 forever. So if you think about these fractions of things, it's saying, well, if you start with fractions, you'll remain with fractions. But also, if one of the populations goes completely extinct, it cannot spawn out of thin air, right? It cannot reappear. Once it's extinct, it's extinct.
They can't go extinct. 0, 1 is the open interval 0, 1 is.
Yeah, it can converge to being extinct, but if it's actually extinct, it never comes back. Right? If you start the system with one of the populations not there, of course, this together with this smoothness will say something about the behavior near the endpoints. Okay, and I'm going to make an irreducibility assumption. So I can't assume, like here, that sigma is positive everywhere. Because if sigma were positive here, I would have a probability of getting out, and that would be bad. So I'm going to ask sigma to be as positive as it could be without violating this. So it has to start at 0, but everywhere else, it's positive.
When you drew, can I extend this sigma smoothly to 1 plus delta? You're going to have a lot of negative. Okay.
I'm not asking that it extends positively outside. Yeah. Just asking that it extends outside. Yeah. Yeah, the positivity assumption is just inside and it extends. Okay. So already a first thing to notice so here what we said was that mu t always converged to this uniquely determined thing. And you can sort of convince yourself that because there are these assumptions here, they're really, for example, there was no measure living at a point that would be invariant under this or anything like that. So anything that had to be invariant would kind of have been to be absolutely continuous with respect to Lebesgue. But here there are different sort of types of measure that live on different dimensional objects that are invariant measures for this diffusion. And there's a general fact for regular enough diffusions, or more generally, regular enough Markov processes, that any limit point of a sequence of empirical measure has to be an invariant measure. Okay, that's a general structural result. So anything that I think is a candidate for being a limit point of this will have to be an invariant measure. And it's a general fact, again, that let me just write what the limit points can possibly be, and then we'll discuss what it means. Okay, so there's always Dirac measures at these points that are invariant measures. So these are always there. And there may or may not be an invariant measure that's absolutely continuous with respect to the. Now you can convince yourself that these are the only possibilities for so-called ergodic invariant measures, and then any invariant measure would have to be a linear combination or convex combination of those. So when you're looking at mu t, you're really just looking at what type of combination of those objects, if this one exists, can be a limit point of my net of empirical measures. So assuming that b prime of 0 and b prime of 1 are non-zero, I can tell you what the limit points of empirical measures would be, depending on the signs of these objects. Okay, so that's a not so hard thing to prove, but it sets the stage for what I'm about to do next. Okay, so let's just think about what can happen in one dimension. No. So I'm making this genericity assumption, or if you want to use more technical language, this hyperbolicity assumption that the derivative of b does not vanish at the endpoints. Then just by looking at the signs of these derivatives, I think you can convince yourself of what is going to happen. So let's start by the top left. If the derivative is at 0 is positive and the derivative at 1 is negative, it means that it's like on this picture. At both endpoints, the vector field is pushing inwards. So you can't really, I mean, you'll have to show it, but I think it's possible that you can't really have your empirical measures converging to a Dirac at 0 or at 1. And you can show that such a measure exists, and then there's going to be essentially the same picture as this in the case where the derivatives have these signs. So when the derivatives are positive at both endpoints, there exists pi, absolutely continuous with the bag.
Did you mean b
Yeah,
prime
yeah.
of 1 less than 0?
Yeah.
Why?
But
Sorry, can you repeat that?
Your picture has b prime of 1 less than 0, b prime of 0 bigger than 0, which is the bottom left box.
I'm confused. If the derivative is positive, it means that it's positive here and negative here. Did I do my expansion wrong?
Should be the box and direction. B prime of 1. That's a decreasing function there.
So it's the blue thing that I'm looking at. If the blue is positive here, that's what pointing to the right means, and negative here, it means that the derivative is positive. I may have gotten this wrong, but I think,
Yeah, I think you said it wrong before, but you wrote it in the right box.
okay, so instead of drawing it like arrows, I can draw B like this, right? Positive derivative means it's negative on the left, so it's pushing me back further to the left, so towards the center. Huh? Yeah. Yeah.
But then at zero, then it's negative. One of the two has to be different.
So here it's also positive derivative, so it's positive here. It doesn't really matter at the end of the day. There is a sign convention that makes this work. But I think this, I mean, that's what I wrote here. So I just.
Works for me now.
It works for you? Good. Okay. So in words, it's when both are repelling, pushing you back towards the center, then there exists a measure such that trajectories explore the whole interval and measures converge to this measure with support on the whole interval.
This doesn't depend on sigma, on how fast goes to zero, like for any.
Well, it can't go too slowly to zero because it has to extend smoothly. So it cannot behave like x to the cube or something like that, right? It has to extend smoothly, so it's at least it has a linear term. Well, it doesn't need to have a linear term. It could be quadratic, it could be cubic, but it cannot be a fractional power near zero. Of course, changing sigma will change this pi, but the qualitative result is that as long as pi is positive inside and is smooth as it approaches the endpoints, then you're good for this. Yeah? Okay. Which one do I want to do? Let's do this one. Okay, so this one, B prime positive and B prime of 1 negative, means, and maybe I'll get it backwards, but it means inwards here and towards the endpoint here. Okay, so what's going to happen then? Whenever you try to go towards here, you're sort of repelled. And you can convince yourself that at least if you start close, there's a positive probability that you go toward 1 and never come back. Well, if it has positive probability here, then by continuity, it has positive probability everywhere you start. So you can say here, there's a lower bound on the probability that if you start in here, you get absorbed towards 1. And then all that's left to show is that if you start close to here, it doesn't take too long to go back to the middle. And that's the thing that's true. So you can write down a Lyapunov function and just show that any interval like this that you write down is actually positively recurrent. And so xt goes to just the point 1. 1 is the only possible limit points of such trajectory. And the only limit points of empirical measures is the Dirac measure at 1. Now, if I reverse the roles, I have this. Yes.
Why is this not in like why is 0, 1 still invariant if you have like a positive probability of going to 1?
Sorry?
Why is 0, 1 like invariant?
Here? Well, in any finite time, if you start in 0, 1, you're still in 0, 1. You converge, but slowly. So you never reach 1 in finite time, but you converge to it. Again, if my B were allowed to not be 0 at the endpoint and not be smooth, then probably I could make it reach infinite time. But with those smoothness and invariant assumption, it's just You go to one, but you never reach it in finite time. Okay. Now the only part that's left is like this and like this. Well, now the statements are not going to look like this. It's not going to be a unique thing that you know you converge to and a unique measure you know you converge to. Okay, that's in the title would correspond to introducing the notion of a random ergodic attractor. So there are probabilities. So let me just write the quantifiers here. For every x, there is P0 of x between 0 and 1, such that xt converges to 0 and mu t converges to delta 0 with probability P0 and the other way around with probability 1 minus P0. Okay, so your guess on with what probability you go to one or with what probability you go to the other will depend on where you start. Because if you start very close to one, you should kind of see that you have a higher probability of being sucked in here than all the way over there. But for every point, there's a positive number between 0 and 1, such that all the dynamics does essentially is it chooses a future between those two ergodic futures. Okay. So there's those two asymptotic behaviors of trajectories and empirical measures, and the noise sort of tells you which of the futures you choose. And there are only two possible futures, and that's it. So that's the first word in my title, random ergodic attractor. So the noise makes you choose at random one of a few possible futures. And now,
What do you mean ergodic?
okay. Yeah, that's a very fair question. An invariant measure for a diffusion is just if you distribute your initial conditions according to that measure and you evolve it forward, the distribution after time t is still going to be that same distribution, right? That's invariant. Ergodic, there are different ways to define it in this context, but I think the most helpful for now would be it cannot be decomposed into a convex combination of other invariant measures. So for example, Dirac measure at 0, you cannot decompose into anything else. Dirac at 1, you cannot decompose into anything else. And here, this pi, when it exists, because of the fact that the noise is positive, you can sort of see that you can go from anywhere to anywhere. And so that rules out that such a pi could be decomposed into. Okay. So a priori limit points, a priori limit points of invariant measure, they're of empirical measures, they're invariant measures, but they may or may not be ergodic. And so right now, all we've seen is you just choose an ergodic measure. Sometimes at random, and sometimes you already know what it is. So now I want to push, get more and more complicated settings in which maybe you even have limit points that are not ergodic measures. Okay, so that's where we're heading next. But so far, all of these limit points that we saw, and in fact, if I want to be consistent with what I said before, I want to emphasize that this is a singleton. There's two things that are important here. There's only one limit point, right? Once with probability 1, it's one of two limit points, but it's not like a sequence has several limit points. It's just you choose a way of converging out of two possible ways. And these things, these limit points, which are here limits, are ergodic. They cannot be further decomposed. And now the idea is that if you start doing this kind of thing, but in higher dimensions, then you can get both random and deterministic and both ergodic and non-ergodic limit points. Okay, so that's part 2. So this is really results about diffusions on convex polygons instead of on line segments. The motivation is probably triangles, but I'm going to write it on the square because the square has the advantage of having a single coordinate system that behaves nice at all the corners, whereas the triangle you sort of have changed coordinates to make the corners nice. So I'll write everything on the square, but it's really about convex polygons or things diffeomorphic to convex polygons even. Okay. So I have the square, the unit square. It has corners that I'm going to label O1 up to O3. It has edges. And it has an interior that I'm going to call bold X0. Okay. And I follow an SDE. Okay, so now I start at a point X and I move according to an equation that looks like this. So to go back to your question earlier, these conditions, just the derivative of B being the sign, these conditions would have been uglier if I didn't use Stratonovich convention. So that's why I'm again writing in Stratonovich convention. Okay. We again assume smoothness. Okay, smoothness means B and sigma extend smoothly to a slightly larger open set. Invariance will again mean that the interior, but also all the edges and all the corners are invariant almost surely. Okay, so for the edges, it's again, in this picture, an edge corresponds to a situation where one of the populations has gone completely extinct, so it cannot come back if it's been completely eradicated. Irreducibility. So I'm going to assume that these sigma 1 and sigma 2 are as positive as they're allowed to be if I want these things to be preserved. So that means that sigma I, so either sigma 1 or sigma 2, is positive when xi is not 0 or 1. So if I think of the noise in the horizontal direction is going to be positive everywhere, except when x1 is equal to 0, then I can have horizontal noise, but I'm allowed to have vertical noise. Okay, so I have as much noise as I can while being consistent with these invariance conditions. Okay, so in this case, I have to start erasing. What are possible limit points of empirical measure, right? What are the possible limit points of the measure describing where you can spend time? So the possible ergodic measures are Dirac masses at the corners. Those are always there. You could have measures on edges mutually absolutely continuous with respect to the Lebesgue measure on said edge. That may or may not happen. Right, because the restriction of the thing on the square to an edge is just something like this. So it may or may not happen. And there may or may not be a measure that's absolutely continuous with respect to the Lebesgue measure on the interior. And so any limit point of the net of empirical measure has to be sort of combinations of these things. And we're going to try to figure out which combinations can happen. In 5 minutes. So again, I'm going to make an assumption of the type that some derivatives are non-zero. So boundary hyperbolicity assumption. So at the corners, I'm going to assume now that the Jacobian of the vector field is non-degenerate, which means it just has two non-zero eigenvalues. So it has determinant non-zero. So in terms of a picture, if you have two non-zero eigenvalues, they can either both be positive, in which case what you have is a source at that corner. They could be one positive, one negative, which means it's a saddle at that corner, or they could be both negative, in which case it's a sink at that corner. Right? What does the behavior of B look like near a corner? Well, it could look like a source, a sink, or a saddle, depending on the signs of the eigenvalues. When well defined, right, I said that a given edge may or may not support an invariant measure. If it does, I'm going to assume that the average of the linearization of the push in the normal direction to that edge is not zero. Okay. So if I go along an edge, B as a component horizontally, it is zero vertically, but it has a first order expansion that's non-zero. So in places it will be positive, maybe in some other places it will be negative. And I'm just asking that these positive and negative contributions do not exactly cancel each other when integrated against the invariant measure that lives on that edge. The other one is when all corners are consistently oriented saddles, the product of the positive and negative eigenvalues are not equal. I'm saying if it happens that all corners are saddles that are consistently oriented, meaning something like negative, positive, negative, positive, positive, like this. The linearizations of the vector field is made of saddle. The eigenvalues corresponding to these saddles are not perfectly tuned. Okay. So that's another sort of generic assumption that avoids some behavior. Okay. So I can state the theorem. And that's, I would say, the main theorem of our paper. It's a three-part theorem. If there is a sink, so one of the corners is a sink, or an attracting edge, okay, so either there's one corner when it's a sink, or there's one corner where a measure lives, and that integral here, which if that helps, you can think of essentially as a Lyapunov, a transverse Lyapunov exponent for the diffusion near the edge. If that's negative, I call the edge attracting. So if you have a sink or an attracting edge, then we face random ergodic attractors. So that just means that there are probabilities corresponding to the different sinks or attracting edges, if there are many. And choosing a future is just you choose one of these sink or attracting edges, the trajectories converge to that, and the empirical measures converge to the ergodic measure that this thing supports. Okay. B. If we have consistently oriented saddles with the negative eigenvalues stronger than the positive eigenvalues, then we finally, in this very special case, get something that's not an ergodic behavior. What does that mean? The trajectories, they converge to the boundary. Okay, so there exists a closed set. That's the set of limit points of the trajectories. And there is a quadrangle of non-ergodic measures such that, and it's again for all x with probability 1, the empirical measures does not have a single limit point as its sets of limit point. It has a whole one-dimensional object living in the space of invariant measure that it keeps visiting in the space of measures. Okay. And C, in all other situations, xt converges to the whole circle, and the empirical measures converge to a measure that lives on the interior and has a density. What did I call this one? Pi interior. Okay, so what we were able to do is give this classification in 2 dimensions of these different types of behavior. And really the only way these limit points of empirical measures can fail to be ergodic measures is in this very particular scenario of a network of saddles that conspire in this way. So we have more information on what this gamma looks like. If you have questions, I'm happy to answer, but I ran out of time, so I'm going to stop here.
We have questions.
Yes?
So this is for 2D, right? Result?
Yes,
You do 3D or trying to do it?
we're trying to do it. So now, okay, so this is what I would call random ergodic. This is unique ergodic. This is unique non-ergodic, right? There's a with probability 1, there's this structure in the space of measures that exists, and almost surely your empirical measures converge to that. We can, in 3D or in 4D and in any other dimension, we can show that these behaviors can happen, right? We can construct examples by using products of these, where you can have a random non-ergodic thing, for example, but we don't have a classification in higher dimension. Yes.
Case B, your team will visit all four the edges. Will be similar to the Birkhoff average centered at each edges in different times.
Okay, I think I can draw it, what's happened. Okay. That's the square. You start somewhere, and then you visit a saddle. And because the negative eigenvalues are stronger than the positive eigenvalues, every time you pass a saddle, you exit closer to the boundary than you entered. And so you keep doing that, where you get, and now you visit the next saddle. Of course, it's not a straight line here. It's a process that takes order one time, where you go to the next saddle. And then you're here, and you're going to end up, when you exit, even closer. And because every time you do this, you get closer, closer in this picture also means slower, because the closer you are to a corner, the weaker the vector field is. So you spend more and more time near each corner. And so you can compute like how much more time do you spend here compared to there, and check if that makes things fail to converge on average, and it does fail to converge. But in the space of measures, okay, I cannot draw in 4D. Let's say it's a triangle instead of, okay. So or even a duangle, like something like that. Okay. So there's, no. Fine. No, but then it won't be a quadrangle. Okay. So it's not gonna be up to scale, but because I'm kind of in infinite dimension. But there are these 4 Dirac measures, right? That are somewhere here.
Is that what you're converging to? Direct measures?
So you're not.
Sometimes one.
So there are these 4 Dirac, like pure at one corner and at the other. Then there are specific combinations of them that give more weight to some of them. Okay, so there are these 4 different combinations of these 4, but that have like a preferred one. And in the space of invariant measure, these 4 things, which are again 4 invariant measures, you can draw straight lines between them like this. So that ends up being a non-planar quadrangle in the space of invariant measures. And what you do is your empirical measures approach this quadrangle and sort of do this more and more slowly. Because you go here, now you start accumulating a contribution which looks like a delta here. So you get, and let's say this is the origin. This is the delta at that corner in particular. So you start moving towards this Dirac. But before you reach pure Dirac at 0 in the average, you start accumulating more of this other Dirac because you've transitioned to here. So you make these transitions, and so it ends up drawing a closed curve in the space of invariant measures. And that's what your empirical measures explore. Your empirical measures does not converge because it keeps sort of switching before you completely reach anything. But that's sort of the dynamical picture. Get closer, as you get closer, it gets slower. So the empirical measures don't converge to anything. And we see that in 2D, that's the only mechanisms by which empirical measures can fail to converge. Of course, there are assumptions. You can draw systems in 2D that where there are the assumptions that I've made fail, but under these assumptions, let's see.
I think there's any real system, like some editor break 3 animals, and they actually do it.
Yeah, so people have observed like, okay, so that would be on the triangle. The fractions sort of seem to be spending more and more time near one corner and then switching to the other and spending a lot of time there and then slower and slower. You can do numerical simulation with some models. Yeah. And you would typically observe that maybe in the growth. Okay, so that's for the fractions, but often like the growth rate of the total biomass is a function of the fraction. So by keeping track of the total mass sort of there are different phenomena, growth phenomena. So switching between different growth regime could be maybe explained by something like that going on at the level of fractions. But I'm not a biomathematician, so that's not exactly but that was some of our inspiration.
Okay, let's thank the speaker.
Danny.
Eigenvalues are
See- see
balanced
tomorrow?
is possible.
Uh,
There is no
Are you
like
good for it? Yes.
spend much
Yes,
time.
I wrote
on that
some
and
stuff
then
up. I'll definitely
more
have
time
some
on
to
this
share.
edge and then more
Very
time on
good.
this edge, so
I
it
have
is
stuff
still
to
an
share, but I'll have more stuff.
Okay,
to
so yeah,
Okay,
so
for-
okay.
for PM.
So if
In person.
so, are you talking about the ratios being exactly one or the positive ones being stronger than the negative ones?
No, being exactly one.
Okay, exactly balanced. It means that for some of them, as you traverse, you'll get closer. Some you'll get further as you traverse in such a way that on average, you don't get neither closer or
You don't know.
or further. And what may happen is that this boundary acts like
If you're visiting all these, then it's the center of the average. Like if you go
we don't know, because this is kind of some weird null recurrent thing. It's like in 1D, right? If my derivative is not zero, for example, if my vector field is zero in a part, I have null recurrent behavior, where like it can take the expectation of going back to the center is like infinite.
You don't get.
So like that opens up a whole can of worms. Like when it's perfectly balanced, it's like null recurrent diffusions.
And when
Thank you so much.
the other one is bigger, the one that push away is.
Then you come back enough to actually the center and you mix, and then you're in that situation here. Yeah.
So what? It's fun.
All three to erase all the board.
It doesn't matter.
Somebody does it at the end of the day.
So one question was, if the sigma and the b is equals one, if they vanish like a fraction of power, can you get like, can you get a more exotic behavior that like?
In general, I would say yes. So if they vanish at the same fractional power, I would be tempted to just change coordinates to make them both. Right? I think what matters most is that they're the same order. And it also works if B is more steep than sigma. You could have like actually no noise near the very end and it wouldn't matter. But if the noise is like stronger than then you're like in the territory of you get a whole bunch of null recurrent stuff kind of. If you have very strong diffusion and no drift too. I think you would probably get like null recurrent behavior.